average height is 6 feet tall, and you know someone in the class is 4 feet tall, what do you know about at least one other person in the class? That they're shorter than 4 feet?
No, that they're tall, because if the average is tall people, then wouldn't that short person be like an outlier or something?
Wouldn't they rise up?
Right, so to balance out the short person, you gotta have a person
More.
that's
Oh, like, yeah, medium or more tall. Taller.
taller than the average. Excellent, taller than the average. Now, I heard you, Abigail. Somebody use Abigail's deduction. What does this tell me? How? You lost it.
We just lost it.
I'll start out the explanation. I will start it and you will finish it for me. Okay? So, if the average density of the whole Earth is 5.54 grams per cubic centimeter, and the density of part of the Earth the crust is lower 2.6 grams per cubic centimeter. Now, finish my thought. Then
Wouldn't the inside be more dense to raise the average?
Then the inside, Leilani's got it. Then the inside must be more dense. To raise the average. Average. Average?
Cabbage.
Average.
Yeah.
Average. There we go. I get very excited. Skip over letters. Okay, so Benjamin Franklin probably knew that the Earth has layers and the inside of the Earth has to be very, very dense because the surface is very not dense. Okay, because the bulk average density is pretty high. Now that's not how we do it today. What we do today is we use seismic waves. Okay, so seismic waves. Where do seismic waves come from? Have you ever heard of seismic waves?
Earthquakes.
From earthquakes. Can be used to determine the materials and structures inside the Earth. So there are a couple wave behaviors we've talked about before. Do you remember what unit we talked about? Reflection, refraction, and absorption? Meteorology, excellent. So we should have, that was first unit, that should be embedded in our brain cells now. What is reflection? What are waves doing in reflection?
Bouncing.
Bouncing, so that's waves bouncing. What is refraction? Waves bending, excellent. And then what is absorption?
Absorbs or taken, changed to another.
Excellent.
energy type.
So it takes in the energy. And transforms it to another form. Okay, so we've got waves bouncing, waves bending, and taking in the wave and turning it into another form of energy. So all waves, including water waves. What are some other waves we talked about in this class? Sound waves, excellent. What other waves?
Light.
Light, excellent. And seismic. Waves can be reflected, refracted, or absorbed.
Well, you can use this.
So, A simple example is an X-ray. So we've got X-rays and sonograms. What is a sonogram?
An ultrasound.
An ultrasound. What's an ultrasound?
Sound waves being used to like make an image.
Excellent. Sound waves used to make an image. And then what are X-rays? When you get an X-ray, that should be fairly straightforward. It's not a trick question.
Look through dense parts of your body.
Excellent. So this is using X-rays. To create an image. And because X-rays are quite a bit more relevant to what we're talking about in this class, in the example we're going to use, we're going to just look at X-rays. Okay? So, you're going to get to giggle at me because you're going to see Dr. Evie's fantastic art skills on parade once again. And all my anatomy and physiology friends will be laughing at me because of my picture being that bad. So, imagine that you have a hand that you're taking an X-ray of. And you shoot X-rays through the hand onto the special type of photographic paper that picks up on X-ray radiation. So these are X-rays. What am I going to see in my photo? You will see bones. Excellent. And this is where the giggle comes in. And bones. There we go. Okay, so those are hand bones. Hand bones. I obviously do not teach anatomy. Okay, bones inside the hand. So why do I see this image of bones? And why, as opposed to a picture of the hand? So why do I see that image of bones on the other side of this?
Because bones are more dense.
Excellent! So bones are more dense. So why does density play a role? Why is that important? What are the bones doing?
Reflecting.
Absorbing.
Absorbing. Excellent. Yeah, so they're actually absorbing, which is kind of creepy, which is why we use sonograms for pregnant women, because we don't want to be shooting a developing fetus full of ionizing radiation. So, so the bones absorb X-rays. Well, soft tissue, in other words, like skin, muscle, etc., allow X-rays through. So, what's that called? When the rays of light actually go through the thing. This is once again a review of a concept back in meteorology. It's called what? When waves, like light waves or sound waves, actually go through the thing.
Transmit.
Excellent, Catherine! To allow X-rays through, be transmitted. Okay, which creates a picture. So in this model, or this analogy, I got 2 seconds, 2 statements. In this analogy, the hand represents something and the X-rays represent something. What does the hand represent and what do the X-rays represent? Remember, we're talking about geology. We're not actually teaching anatomy and physiology. I don't know that class. That's one of the things I do not know. So, that is the worst hand bone drawing on earth. So, We relate this back to what we're talking about in geology, back to the earth. What does the hand represent in this analogy? What do the X-rays represent in this analogy? Maybe someone who I haven't heard from before, who could probably use coffee. A lot of you look like you would benefit from a cup of coffee. I've got a Monster right here. I'm not recommending that, but definitely keeps me chipper. So what do the hand represent and what do the X-rays represent? Yes.
Does it have the crust?
Good start. A little bit more expansive than the crust. All the earth. Excellent. So the hand represents earth. Because we're talking about what's going on. How do we know what's going on deep inside the earth? So the hand represents the earth. What do the X-rays represent?
Wouldn't that be the crust then? The seismic waves?
The seismic waves. Excellent. Because we're talking about seismic waves building the picture, right? So this is an analogy to help understand how waves, this isn't a non sequitur where I'm going into suddenly like, Dr. E, do you remember what class you're teaching? You're not teaching anatomy and physiology or you know, what's that study called? Radiology? Is that where they do the X-ray science? Anyways, so no, we're doing geology. So the hand represents the earth, the X-rays represent the seismic waves. So, very similarly, seismic waves can be used to build a picture of the inside of the earth. Now there are 4 major types of seismic waves. P, S, L, and R. Now just so you know, P and S are the ones you'll need to know. And understand, L and R, you just need the names. Okay? So you don't need to like memorize a bunch of different features about L and R waves in your book. You just need to know that L and R waves exist and fall into a particular category of wave. So these waves fall into 2 categories, body waves and surface waves. Body waves pass through the earth. Now, looking at that definition, what do you think the surface waves do?
Travel on the surface.
Stay on the surface. Excellent. Now, the 2 body waves are P and S, and the surface waves are L and R. Now, this pretty much summarizes everything you need to know for this class on L and R waves. Boom, you are done. There's 2 other types named L and R and their surface waves. Now, I'm going to go ahead and I'm going to X out sections in here. I do write all my own notes, but I have been known to copy paste from other classes. So there's more blanks here than y'all need. So you don't need to know how to remember. You don't need to know all those details of L and R waves. You just really need to know P and S waves. So let's first fill in this column. For P wave, I would put, are you awake? From P wave, I would put, this is an are you awake test. Body, excellent. What about S?
Body.
Body. What about L?
Surface.
Surface. And what about R?
Surface.
Surface. Now we're going to go into how these waves actually move. And this is when I get to play with a slinky. This is my slinky. Do you see my slinky?
It's right over here.
It's right over here. It went wandering. I was probably, sometimes when I get distracted or I'm wandering around doing a test, I play with my slinky. Same thing happens with my silly putty. Good work is like play. Okay, so we're going to use a silly putty to illustrate the different motions of the P and the S waves. So P waves are also known as pressure waves because, so how are we used to waves moving? Can someone, show me with your hands, how do waves move? Waves like water waves. I like yours, Caitlin, like the okay, so that's how water waves move. And that's how S waves move too. Okay, they move exactly how you're expecting, up and down like this, like water waves. However, P waves, because they're pressure waves, move a little bit differently. So with a P wave, what you have is that it's a pressure squeezing as it moves down. So I'm going to generate a pressure wave. Everyone see that squeeze in the slinky as it moves down? Let's see if I can get, oop, a little contour would help. Ah, it's not working. Ah, what did the wave just do?
Bounce back.
Bounce back. What's that called? Reflection. Excellent. We even got a pressure wave reflecting. Excellent. So there's a lot of waves that we encounter in everyday life that are actually, in fact, pressure waves. What the most common one is sound. Sound is a pressure wave. And if you're here, how many people, well, I don't even have to know how many people. If you're here in February, we have Super Science Saturday, and I have a spectacular demonstration of pressure waves that involves like techno music and fire. So it's called a Rubens tube. It's pretty awesome. So pressure waves, P waves are pressure waves, and they move by squeezing. S waves are what's called shear waves, and they move up and down. Now, P waves are the fastest wave, while S waves are the second fastest, a little bit slower than P waves, and L and R waves, which are both surface waves, all surface waves are slow. Now, how do I remember that P waves are P waves and they're pressure waves and they're you know, they arrive first, and S waves are shear waves and they're slower and they arrive second. So P waves are primary. What does the word primary mean? First. Excellent. So first, primary pressure waves. Well, S waves are secondary shear waves. And luckily, P waves are actually, the P stands for primary and S stands for secondary. That's actually where they came from. It's actually very convenient that they match up also with the shear and pressure qualities as well. So that hopefully that'll help you remember. And throughout this portion of the unit, because there's a lot of weird little terms that are easy to get mixed up, I will bring up some mnemonic devices, some ways to help you remember the terms. If they help you, use them. If they don't help you, I'm not testing you on mnemonic devices. They're there to help, okay? So if you're not helpful, don't worry about them. So if we're going to understand earthquakes and try to understand how earthquakes work, it's useful to understand what one of these guys is. Okay, so this is a recording of an earthquake known as a seismogram. Well, a seismograph is the instrument used to make the recording. Okay? It senses the seismic waves. So the seismograph is the device that senses the seismic waves. The actual recording itself is called a seismogram. So if you're going to take about 5-10 seconds, fill in the blank, get them straight. And then we will talk about it. Go ahead, take a guess. It's easy enough to fix if you guess wrong. So what goes in the first blank? Seismogram. And the second one is seismograph. Excellent, and that's the correct order. Now to remember that the seismogram is the wiggle picture, whereas the seismograph is the device that makes the wiggle picture. The way that I have always remembered it is that, to me, the little M on the end of seismogram looks like P and S waves and surface waves in the seismogram. Okay, so that little M, every single time I look at the words, I still think of that back to undergraduate. And little M is a little wiggle. Huh?
I have another one.
What's another one?
Instagram.
Instagram. So Instagram, the gram is the picture. There you go. It's another one. Another good one. So the problem is, like, a photograph is, yeah, that's kind of confusing. But Instagram, that's a good one. So here we have a picture of a what? Seismogram or seismograph? Seismogram. Now, next time we are together, we are actually going to be doing a plate tectonics activity, okay? And we'll start out in here and then move to the room next door to do the activity. And look at, what's the title of the activity?
The cookie model.
Cookie models of plate tectonics. Okay, so we'll talk about the layers of the earth, build some cookie models out of cookies. Well, graham crackers. And those are kind of cookies. The line between cracker and cookie is very thin and not poorly defined. So we will be doing that, and then we will wrap up our earthquake discussion, and then the last activity we're doing is a mapping activity, and then we're done with Unit 4. Holy cow! We went zippity-doo-dah through that. Oh, one last announcement. If you would like to see me get a pie in my face, PTK is doing their Pie of Professor, and I won Pie of Professor. I am going down there to the Commons in just a few moments to get pied in the face, and all the money donated goes to Watertown Urban Mission. So, want pie in the face, pay $5, boom, pie in the face. Sure. Yeah. That's why we take notes like this. You want to go grab it and sit down?
And the extra credit thing is